Hey everyone, welcome back to The Explainer. Today we're diving straight into the invisible architecture of our modern world, the hidden chemical chains that literally build everything around us.
I mean, seriously, just take a look around you right now. Everything from the plumbing hidden inside your walls to the clothes you're wearing, and even what we're looking at right here, a life-saving Kevlar vest and some seriously heavy-duty polypropylene rope. It is all tied together by one absolutely brilliant chemical concept: polymers.
So here's our roadmap for today. We'll start with a welcome to polymer world, look at 2 ways to build these chains, decode and design plastics, tackle the environmental challenge, and finally look at how polymers are actually saving lives.
Let's jump into Section 1, Welcome to Polymer World, the building blocks.
Now, as you probably already know, the sheer power of polymers really comes down to their massive scale. The word itself literally means many parts. Think of monomers as these tiny individual chemical links. When scientists, or nature itself, snap these molecules together through polymerization, it creates these massive, heavy-duty chains. And this process completely revolutionized material engineering. It's what makes modern structures affordable, super lightweight, and just incredibly durable.
Moving right along to Section 2, 2 ways to build chains, the chemical reaction.
Okay, so there's a really stark contrast between the 2 main ways we actually fuse these molecular links together. First, we've got addition polymerization. This is where monomers just add onto each other, one by one, without losing a single atom. The double bonds just pop open in this continuous chain reaction. But then, look at condensation polymerization. This one forces a small molecule, something like water or hydrogen chloride, to literally be squeezed out or eliminated every single time a new step-by-step bond forms. And this underlying chemistry totally dictates the physical properties of the materials we get. When ethene opens its double bonds in an addition reaction, it yields this simple, soft polyethene, the stuff we use for basic shopping bags. But contrast that with the condensation reaction we use to make nylon 6,6. By combining different monomers step by step, you get this unique structure that gives us a much harder material. It has a smoother surface, insane impact resistance, which is exactly why it can take the brutal shock of being used in skateboard wheels.
Which brings us to Section 3, decoding and designing plastics, from rigid to flexible. So the really cool part is how just tweaking these chemical recipes completely alters the everyday materials we rely on. Take polyvinyl chloride, or PVC. In its pure, rigid form, it's super stiff, it doesn't bend, it resists weathering, it's basically perfect for heavy-duty water pipes. But we can actually hack it. By adding these chemicals called plasticizers, we weaken the strong forces between the polymer chains. Suddenly, those microscopic chains can slide and move around much more freely. Boom! You've instantly transformed a stiff, solid pipe into flexible, shapeable tubing, window frames, or even medical catheters.
It's honestly incredible that one single chemical structure handles all of these wildly diverse applications. I mean, from rigid foam boards to flexible garden hoses, all the way to the soft cling film you use to wrap your leftovers. It really just depends entirely on how those internal chains are designed and spaced out to move.
And similarly, nylon's incredible range makes it an absolute powerhouse of a polymer. Because of its high tensile strength, its elasticity, and its tough resistance to wear and tear, you'll find it woven into waterproof activewear and fishing nets. But it's also tough enough to be molded into heavy-duty industrial gears, bearings, and even automotive parts sitting right under the hood of your car.
Now, you might be wondering, what if I want to figure out what a specific plastic is actually made of? Well, you can basically become a polymer detective by working backwards. Step 1. Check the backbone. If the main chain only has carbon atoms, you're looking at an addition polymer. But if you spot oxygen or nitrogen in that main chain, it's a condensation polymer. Step 2, identify the functional linkage, like an ester or an amide. And finally, Step 3, isolate that repeating sequence, and you found your original monomer building block. It's this absolutely crucial reverse engineering process that lets material scientists break down and recycle complex industrial plastics.
But of course, we have to talk about Section 4, the environmental challenge, the dark side of durability.
Because here's the catch. The very trait that makes polymers so incredibly useful, that indestructible, unreactive nature, has created an absolute massive global crisis. Conventional polymers like polyethylene are chemically inert. They just don't react with much. Now, that is fantastic for safely storing a jug of milk, but it's terrible for the Earth. They just pile up in our landscapes and our oceans, taking up immense amounts of space. And the worst part? Over time, they don't even fully decompose. They just fracture into these tiny, harmful fragments we call microplastics. These spread through the soil, they contaminate our water, and eventually they make their way right into the food chain, posing some serious risks to marine life and human health.
But science is actively striking back here. First up, we have biodegradable polymers. By incorporating natural materials, like starch, right into the plastic matrix, soil bacteria can literally eat and decompose the material much faster, breaking it down into non-toxic compounds. And second, we have photodegradable plastics. Chemists have actually engineered these chains with specific functional groups that act almost like targets for UV sunlight. So the sun's added energy weakens the bonds, causing the plastic to literally shatter and break apart just by being left outdoors. How cool is that?
All right, moving to our final section, Section 5, Polymers Saving Lives, Biomedical Engineering.
This is perhaps the most uplifting application of this entire field of chemistry, how these incredibly versatile materials are quite literally saving human lives every single day. Now, polymers used inside the human body have strict requirements. They absolutely must be completely biocompatible, meaning they cannot cause allergies or trigger rejection by the immune system. So for things like artificial blood vessels, doctors rely on PTFE. It's a polymer that is so incredibly smooth, it actually prevents dangerous blood clots while safely bypassing blocked vessels. Meanwhile, for something like an artificial heart valve, they use specialized polyurethanes and silicone. Why? Because these specific polymers are highly flexible, incredibly durable, and capable of withstanding a literal lifetime of constant, non-stop motion inside a beating human heart.
So, seeing both the devastating environmental impacts on our beaches side by side with these literal life-saving medical marvels in our hospitals, it really leaves us with one vital question to ponder. From polluting our oceans to pumping our blood, how will we choose to design, use, and shape the polymers of tomorrow? Ultimately, the chemistry is right there in our hands. Thanks for exploring the science of polymers with me on this explainer. I'll see you next time.